Okay, so now we are asked to apply the vertical line test. And so it says use the vertical line test to decide whether the graphs in this figure represent y as a function of x. Well, if we look at our first graph here, we got a sleepy parabola. You can see that we can draw a vertical line that touches two places on our graph. So this is not a function. It's not going to work because I can get two different outputs for the same input, which is not what I want. For our second example over here, we have what looks to be like either some sort of sinusoidal function or a cubic function. But anyway, we need to look and find a place where we have two intersections with the same vertical line. Here, it doesn't appear that there's any place that overlaps itself. We can only connect a vertical line with one place on our function, so this is indeed a function of x. And then finally we have some little bit different looking function. It's split up, it's not continuous, but that still doesn't matter. What we need to look for is there any place that overlaps? And you could draw a vertical line anywhere, but it only is going to touch at one place. So this is also a yes. So this is the visual way for us to determine if it's a function or not. Now, it doesn't matter if it's at only one place or two places. Anywhere where we can draw a vertical line that does that. If we can do it anywhere, then it is not a function. So now let's look at what we need to do about finding zeros. So zeros are analytical things. They're not necessarily intercepts. Intercepts have to be real numbers. But we are here and we are trying to figure out what are the zeros of each function. So let's look. A gives us that f of x equals 3x squared plus x minus 10. So this would be a prime time to do the quadratic formula, where we would get -1 plus or minus the square root of 1 minus 4 times 3 times -10 all over 6. And that's going to be x equals. So we should get x to equal -1 plus or minus the square root of 121 over 6, which 121, square root of 121 is the same as 11. So we end up here getting either 10/6 or -12/6. So it's going to be 5/3 or -2. So those are two zeros for that. X would have to be either of those to make the whole thing 0. For b, we end up with g of x equaling the square root of 10 minus x squared. There's just one term that has an x in it, so it's going to be very useful to us to go ahead and just simply solve it. If we square both sides, we're going to get 10 minus x squared equals 0. And so that from there you get x squared to equal 10. So x would be positive or negative square root of 10. And so because it's just got one term with x in it, it's very easy for us to just go through and solve, use simple solving techniques. And c gives us that h of t is 2t minus 3 over t plus 5. Now when that equals 0, the only thing that can make a fraction 0 is if the numerator is 0. You could think about this as multiplying both sides by t plus 5. T plus 5 times 0 is the same thing as 0, right? It goes away. But in a sense, you're shifting this over. It kind of cancels itself out. And so what you're going to get is just 2t minus 3 equals 0. You don't even need to pay attention to the denominator at all. You can just go straight to the numerator. And so from here you get 2t equals 3, or t to equal 3 halves. So picking the appropriate strategy is very important for finding zeros, but just knowing that you're looking for the complexity. Some of them look more complicated than they really are. You just have to make sure you're counting the number of terms, you're seeing the things that are possible, because each one has a very quick way about it.